Okay, so the next topic is about electronic structure. So electronic structure determines how atoms bond and behave chemically. It is one of the most tested topics across IMAT. So we will be going from base to the complex questions, and how many questions and how many types of questions could be asked from this question. So the first thing that you have to know is that how electrons are found in an atom. So the first thing that you have to know is about, like, a common example is about your location. Your location is the best example that can be used to find an electron in an atom. So let me ask you a thing, like if I ask you where do you live, and you will be like, I live in Europe. And I will ask you where do you live in Europe, and you will say like, I live in Italy. And I'm like yeah bro, but where in Italy? And you will be like, in Italy I live in Rome. And I will ask you, yeah, Rome is a big city, where do you live? And then you will tell me about your street, and I will ask you, yeah sure, but like which street, which house? And then you will exactly tell me about your house number. So that's how you can know the location of any person in the world, right? Same is for the electrons. For electrons, first you have to know that the electrons are revolving around the atom. But where do they are revolving? The first thing that you should know is that the first thing is shell. Just like Europe and Italy and Rome, shell is really broad. The electron could be here or here or here. It could be anywhere, right? But if we break down shell into smaller parts like this, now you have a more specific location. The electron could be here or here or here, right? So this is called subshells. But still you are not really accurate. So what will you do is that you will break down subshells into more specific and more narrow paths, and those paths are called orbitals. And orbitals are the place where finding the chances of electrons is maximum. Like highest chance of finding an electron could be in an orbitals, because you are like really specific. I mean, if you are standing in a street, like for example, if I'm living in a street number 26 in Pakistan, then finding my house is not that hard. And if I'm living in Italy and Campania, Luigi Vanvitelli, then finding my classroom is not that difficult, right? So that was the whole story for shells, subshells and orbitals. So if you talk about orbitals, then there are types of orbitals, shells. So let's talk about first of all about the shells. So there could be like shell N1, N2, N3 and N4. They are also called K, L, M and N shells. So the number of electrons in the shells are specific, like K shell could have 2 electrons, L have 18, M have 18 and N has 32 electrons. We'll be discussing about how to memorize the number of electrons really in great depth, so you don't have to be really worried about this. And the next thing that you have to know about is subshells. So subshells are of 3 types. I'm sorry about that, 4 types. So the shells are S, P, D and F. S is for spherical, P is for dumbbell, D is complex and F is very complex. Like these are the shapes of these subshells. There are also names that are written down for these. Like what does S means? S means sharp. Let me write it down for you. So S is sharp, P is principal, D is diffused and F means fundamental. So these are the actual name for S, P, D and F. So spherical is the shape of S orbital, dumbbell shape is for P orbital and double dumbbell or complex is for D orbital. You can also say that the shape of D is sausage shape. And for F it is really complex. If you want me to write down for you, then S orbital is spherical, P is dumbbell shaped, and D is double dumbbell like this. And F is like really complicated, and I won't be drawing it for you because it's actually really complicated and you won't be finding the diagram for F orbital in any high school book. So now you know about the basics for shells, subshells and orbitals. So let's move on to our next topic, that is for atomic number. After understanding atomic numbers, you will have a better understanding for shells, subshells and the orbitals. So the first atomic number that you have to study is principal quantum number. So principal quantum number is the first atomic number. Principal quantum number. So what does quantum numbers actually use for? Just like we used locations to find out the location of electrons, principal quantum numbers are used to explain the behavior of electrons. And to understand the behavior of electrons, there are 4 quantum numbers. The first quantum number is principal quantum number. So what does the principal quantum number gives the information about electrons? It tells you about atomic radius. So the greater the number of principal quantum number, the greater would be the atomic radius. The next property or the next thing that a principal quantum number tells you about is the energy. The greater the principal quantum number, the greater would be the energy of the electron. And the next thing that it tells you about is the distance. The greater the principal quantum number, the greater would be the distance of electron from the nuclei. Distance of nuclei. So for example, let's get this from the shell numbers. For example, the first shell is K, second is L, third is M and the fourth is N. So if I draw out all the shells here, the first is N equals to 1, that is K shell, right? And then I draw out N equals to 2, that is L shell, like this. And then I draw another shell, that is N equals to 3, that is M shell. As you can see, as the number of N is increasing, the electron is getting far and more further and further up away from the nucleus. So as the N shell is increasing, the atomic radius is also increasing. As the number of N is increasing, the distance from nuclei is also increasing. And what about the energy? Whenever an electron jumps from higher to lower shell, it releases energy. So that's why whenever an electron jump from higher to lower and lower, it will keep losing energy. And when it becomes to the first shell, that is the most closer to the nuclei, it had lost most of its energy. And if an electron jumps from lower orbit shell to an higher shell, it will absorb energy. And as it will go further and further away from the nucleus, it will keep gaining an energy. So that's why the N number of N is directly proportional to energy. Like third shell will have more energy, fourth shell will have more energy, and so on. So that's what you will know about the behavior of electrons from principal quantum number. The other things that you can know from here is that there is a short trick that you need to memorize, and that is group number and period number. You will be discussing it in periodic table lecture in detail, but we will discuss it here too. So the group number tells you about number of electrons in a shell, number of electrons. And what about the period number? So the period number tells you about the highest value of N, that is principal quantum number, highest value of N. Principal quantum number is also shown by N. That means the shell is discussed in principal quantum number. We just discussed everything about shell in principal quantum number. So this was a shortcut formula or a cheat code that you can use in your IMAT exam. Don't worry, we will be discussing more of these. Like if you have to memorize the number of electrons, like if you have a trouble memorizing number of electrons, the short formula is 2n square. And if you want to memorize number of orbitals, then the formula is n square. Let's do some examples so you can use this formula efficiently in IMAT. So let's go back to our table. The first table is showing you the number of n's. For example, for the first shell, the n equals to 1, and the maximum numbers that number of electrons that are written there are 2. So the formula that you just memorized was number of electrons equal to 2n square. Let's use that in this table. 2n square for n1 what could be 2n square. So 2n square, you can write it down as 2. What is n? It is 1. So 2 multiplied by 1 raised to power 2, it would be 2, right? For the second shell, you can use 2. The n is 2, so you will put it down in the formula. You will get 2 multiplied by 2 squares. 2 square is 4, 4 2s are 8, so the number of electrons are 8. For the third shell, you will use the formula. The n is 3, 3 to power 2. 3 square is 9, 9 2s are 18, so the number of electrons in third shell is 18. For the fourth shell, you can use the same formula again. 2 4 square, 4 square is 16, 16 2s are 32, so the number of electrons in the fourth shell is 32. And you can keep using this formula for so on. Like you can use any number of shell, and you can use this formula in any shell possible. What about the number of orbitals? Sorry about that, I just wrote the formula wrong. The number of orbitals are equal to n square. So that was about the shortcut formulas and the thing about principal quantum number. Let's move on to our next quantum number. So our next quantum number is azimuthal quantum number. Azimuthal quantum number. As we studied about shell in principal quantum number, we'll be discussing about subshell in azimuthal quantum number. So azimuthal quantum number gives info about subshells and shapes of orbitals. Shapes of orbitals will also be discussed in azimuthal quantum number. Not about orientation or degeneracy of orbitals, but just the shape of orbitals, because shape of orbitals are defined by the subshells, so that's why it is related with the subshell part. So the shapes of orbitals, we have already discussed them in our recent table that was about SPDF. You know that the shape of s orbital is spherical, p orbital is dumbbell, and for d orbital is double dumbbell or sausage or complex, while for f it is very complex. So azimuthal quantum number tells you about subshells and shapes of orbitals. So the shortcut formula for azimuthal quantum number is number of electrons and number of orbitals. The formula used here is also really easy. So number of orbitals could be found as 2l plus 1, and for the number of electrons you will multiply the whole formula with 2, that is 2l plus 1. So as you can see that number of orbitals is always half of number of electrons. The reason is that one orbital can always and only have 2 electrons. There are always 2 electrons in one orbital. Like there can't be more electrons in orbital than 2. 2 is the maximum amount that our orbital can hold. So that's why in every formula for orbitals the number of electrons will be multiplied by 2. Like number of orbitals in subshell, the formula is 2l plus 1, then the number of electrons would be 2l plus 1. So what is L? So L is actually the azimuthal quantum number symbol. The symbol for principal quantum number was n, and the symbol for azimuthal quantum number is L. So what does L signifies? So L tells you that it can start from 0 to so on, and it will always ends on n-1. Like if the principal quantum number is 2, then the azimuthal quantum number is going to be 1. If the principal quantum number is 3, then the azimuthal quantum number would always be 1. So how can we find number of electrons in different subshells and orbitals? So the formula is simple. First you have to memorize the value of L for S, P, D and F. The value of L for S is 0, for P it's 1, for D it's 2 and for F it's 3. If you put these formulas in these, then you can easily find the number of electrons and orbitals. Let's use this formula, that is 2L plus 1. So 2, the L is 0 plus 1, you will get 1, right? If we put this formula in here, you will get 2 multiplied by 1 plus 1, you will get 3. And if you put it here, you will get 2 multiplied by 2 plus 1, you will get 2 2s are 4 plus 1, 5. And for F, you will get 2, the L is 3 plus 1, you will get 2 3s are 6 plus 1, 7. So these are the number of orbitals in these subshells. And what about the number of electrons? You will just multiply it with 2. The number of electrons in S shell are 2 electrons, and in P shell you will get 6 electrons. In D orbitals you will get 10 electrons, and in F shell you will have 14 electrons. So that's how you can memorize and write down the number of orbitals and number of electrons in specific subshells. So that was all about azimuthal quantum number. The next quantum number is magnetic quantum number. Magnetic quantum number is shown by M. It gives you information about orbitals, orientations of orbitals, and degeneracy of orbitals. So these are the information that will be given by magnetic quantum number. And degeneracy of orbitals. Sorry, it's orbitals, not electrons. So now you know that what does the magnetic quantum number is telling you. The formula for magnetic quantum number is simple, that if you know what is azimuthal quantum number, you can just write it down as M equals 2L plus 1. You will get magnetic quantum number. That is the same formula as the number of orbitals, but you have to memorize this too, that if you want to find magnetic quantum number, then this is 2L plus 1. But that is, the answer is not going to be, for example, if you get the answer to be 5, so 5 is not the magnetic quantum number, but 5 is telling you about the number of magnetic quantum numbers. For example, if you are given that the azimuthal quantum number L equals to 2, so if you put the formula here, what you will get? You will get 2 multiplied by L, that is 2 plus 1. What would be the answer? That would be 5, right? But that is not the magnetic quantum number. The magnetic quantum number would be 0 plus 1 plus 2 and minus 1 minus 2. So 1, 2, 3, 4 and 5. So these are all the magnetic quantum numbers. And what do they signify? They are signifying the orientations of the orbitals. For example, if there is an electron that is in the subshell number 2. So what could be the orientation of electrons in that orbitals? So there could be like 5 different orientations of that orbital. What does it mean? It could be written down as like this. It could be written down as this or this or this. There could be like 5 different possibilities about how you can draw or the orientation of electron could be. So that is how and what magnetic quantum number gives you information about. I'm not going into really deep depth of these topics because they are not directly related in IMAT, but you should know the basics of these because they are really important to understand the behavior of electrons. So now you know what magnetic quantum number is. The last quantum number that you will be discussing about is spin quantum number. So what is spin quantum number? As the name is telling you about, spin quantum number tells you about what is the spin of an electrons. It is denoted by S. So the spin of electron could be clockwise or anti-clockwise. If the sign is positive, that is 1 plus 1 by 2, or it could be negative. It is telling you that if it is positive, then the electron is revolving in clockwise or rotating in clockwise motion, and if it is negative, it means it is rotating in anti-clockwise rotation. So that is all the spin quantum number is telling you about. So this was all about the quantum numbers, and we just studied about everything that was to be about electrons. The spin quantum number tells you about what is the shell that electron is present in, and what would be its radius, its energy, its distance, what the group number tells you about electrons, what does the period number tells you about the electrons, what could be the number of electrons and number of orbitals in a shell. Then we studied about azimuthal quantum number that tells you information about subshells, the shape of orbitals, what could be the number of electrons in a subshell, number of orbitals in a subshell. Then you also studied about what could be the number of electrons in subshells, in orbitals, and then you have to know that the number of electrons in orbitals is always 2. What the number of electrons in sp, d and f are 2, 6, 10 and 14. What is magnetic quantum number? What it tells you about the orbitals, orientation of orbitals and degeneracy of orbitals. The last thing that you studied about was spin quantum number. Spin quantum number tells you about the rotation of electrons. It could be clockwise or it could be anti-clockwise. Now let's get back to our topic that was about the 3 rules of electronic configuration, because now you can understand the electronic configuration in the best way possible. So the first electronic configuration is about Aufbau Principle. So what does Aufbau Principle tells you is that it means that the filling of electrons is always in increasing energy level, like the lowest energy of electron will be filled in the lowest one, and then the shell which has highest energy will be the filled next. That means the filling of electrons occurs in ascending order from the lowest to highest. But the problem for Aufbau Principle is that it is applicable to all of the possibilities, but it does not applicable to like in excited state. For excited state, the Aufbau Principle is not applicable. So let me write it down for you. In excited state, it is not applicable. Okay, so that is an exception. So let's discuss Aufbau Principle in here. For example, if you have n value of 1s, 2s and 2p, how can you memorize the energy levels? So first of all, the general rule is n plus l. So the n plus l rule will tell you which electron will be given to which value. For example, what is value of n here? The word that is written here is actually the value of n. And what is the value of l? S, p, d is written along the denominators that you have been given here. So the value of l for s is 0. 2 is the value of n, and value of s is 0. We just memorized the whole table that for s the value of l is 0, for p it's 1, for d it's 2, for f it's 3. We are just using that formula again. The n value here is 2. What is the value of p? It's 1. So just add n plus l. So what is 1 plus 0? It's 1, right? So what is 2 plus 0? It's 2. So what is 2 plus 1? It's 3. So as you can see, we are filling electrons in an ascending order. So the first electron will be filled in this shell, and then in this shell, and then in this shell. You memorized a table when you were in high school. The table was 1s, 2s, 2p6, 3s2, 3p6. That table was given to you and you had to memorize it, but you don't have to memorize the whole table. There is a really easy way to memorize the table. So first write it down: 1s, then 2s, 2p, 3s, 3p, 3d, and then 4s, 4p, 4d, 4f, and then 5s, 5p, 5d, and 5f. You can go up to as many numbers as you want to, but I will just stop it here. So the first electron will go into 1s, the second electron will go into 2s, the third will go into 2p and 3s. Just watch out where the arrow is going. Okay, so the next electron will give to 3p and then 4s. The next electron will go into 3d, 4p, 5s, and then 4d, 5p, and then if there was a 6s here, then it will go into 6s, 6p, 6d, and 6f. You can't go further from 6f because f is the last point here. So let's write it down, these examples first. So the first electron that went to was 1s. So 1s was the first example, 1s. Then it go to 2s, and then 2p, and then 3s, and then 3p, and then 4s, and then 3d, and then 4p. Like, I think these are the enough examples. So the energy in all of these are increasing. So electrons are filling in shells in increasing order. I think you got the point, but I will still explain it in more detail because I know so many students are going to get these MCQs wrong. So 1 plus 0, 2 plus 0, 2, the value of L for P is 1, 3 plus 0, and then 3 plus 1, 4 plus 0, and 3 plus 2, and 4 plus 1. So these are all the values. You will get 1, 2, 3, 3, 4, 4, 5, and 5. So these are the all values that you need to know about these values. So the first problem arises here is that there are some values that have same n plus L value, like 4 and 4 and 5 and 5. So if they have same n plus L value, where would the electron go? Like they also had 3 and 3, because we know that if there is a bigger n plus L value, then the electron will go towards the element towards the shell which has low n plus L value. Then it will go towards the one that has higher n plus L value. But if two shells have same n plus L value, then the electron will go towards the one that has smaller n value. This one had smaller n value and this one had smaller n value. So the electron went towards the one that has smaller n value. So you don't have to memorize all the n plus L values. You can use that into the MCQs. You can also use this table that I gave you. So these are the two ways that you can use to understand in which shell the electron will fill up first. For example, the first shell to be filled is going to be 1s, then second shell that to be filled would be 2s, then 2p will fill, and 3s shell will fill, and then 3p, and then 4s, and 3d you can say it for here, then 5s, then 4d, then 5p, and then 6s. So that's how electrons are filled in an atom. That was about the Aufbau principle. The next principle that you have to study is Hund's rule. So what does the Hund's rule tell you about? Hund's rule tell you that if there are electrons, for example, you have 1s, 2s, 2p. What am I doing? Let me write down again. If you have 1s, 2s, and 2p, as you know that p has 3 orientations, right? You just memorize that in the table above. That is, you can write them down as 2px, 2py, and 2pz. And what are the number of electrons that are filled in p orbitals? The p orbital can have 6 number of electrons. So there would be 2 electrons here, 2 electrons here, and 2 electrons here. S has 2 electrons and 2 electrons. So the problem here is that what if the number of electrons in p orbitals are 4, 2px, 2py, and 2pz. If it has 2 electrons like this, it also has 2 electrons like this, and it has 0 electrons. So the Hund's rule tells you that this is wrong. Hund's rule tells you that the correct electronic configuration would be 2 electrons in this shell, and then you will have 1 electron in this shell and 1 electron in this shell. Why is that? Because this type of electronic configuration is more stable than the previous configuration, because in this configuration there were 2 electrons in one, but there were 0 electrons in the other one. So as you can see, there was a really big difference in both of these. So that's how an atom becomes unstable. To stable out the whole atom, what they did that they balanced out the number of electrons. There were 1 electron here and 1 electron here. So that's what Hund's rule is telling you, that there could be 2 electrons in same orbital, but if there is an empty orbital, then they will go to that separate orbital. The example here is given for nitrogen, as it has 3 electrons, so there will be 3 separate p orbitals, and each orbital will get 1 electron. Not one orbital will not get 2 electrons, because that will be like discrimination with other orbitals. So that's what Hund's rule is trying to tell you. The last is about Pauli's exclusion principle. So the Pauli exclusion principle tells you that there could be only like 3 correct identical numbers. What does it mean? That, for example, let's get to our location diagram. There could be like, for example, if we compare each other, for example, you cleared IMAT and now you are in Italy, and your friend also cleared IMAT and both of you are in Italy. Both of you are in Europe, right? And both of you are in Italy, and both of you might get into Rome, right? But there is a high chance that you guys don't get to study in the same class, but there might also a chance that you guys don't stay in the same house. So there could be so many same things between 2 people, but there is still a thing that is not same for both of these, is that they are not going to be sleeping in the same room. Even if they are sleeping in the same room, then they are not sleeping in the same bed, right? So that's what Pauli exclusion principle is telling you. For example, if there are 2 electrons, they can have same principal quantum number. They can be in a same shell. The second quantum number is azimuthal quantum number. That tells you about subshells. Like if they are in same shell, they can also be in the same subshell. And the third quantum number was magnetic quantum number. Yes, they can be in the same orbital. Like they could be in the same orbital, but the problem is the fourth quantum number. If they are in the same orbital, like let me write it down here. even if they are in the same orbitals, they can't have the same spin. They must have opposite spin. So that means there could be only 3 quantum numbers that could be same for 2 electrons. They can have they could be in the same shell, they could be in the same subshell, they could even be in the same orbital, but they can never have same rotations. One have to be in clockwise direction and one has to be in anti-clockwise direction. That's how 2 electrons are stable in an orbital. If they have same spin in an orbital, like if you write it down like this or like this, they can never have this kind of spin. They must have an opposite spin. So that is what a Pauli exclusion principle tells you, that no 2 electrons in an atom can have same identical quantum numbers. They can have up to 3 same quantum numbers, but not all 4. So each orbitals hold max 2 electrons and they must have opposite spins. One should be have arrow in the upward direction and one should have the arrow in the downward direction. So I think we just connected all the properties of electrons with all the quantum numbers and we made it really simple for you. So let's write down the electronic configuration for some atoms. For hydrogen you have 1s1, for helium it's 1s2, for carbon 1s2, 2s2, 2p2, for nitrogen it's 1s2, 2s2, 2p3, for oxygen is 1s2, 2s2, 2p4. You can write down all the electronic configuration by using this graph, right? Like the first electron will go into 1s, then 2s, then 2p, then 3s, then 3p, then 4s, 3d, 4p, 5s, 4d, 5p, 6s, then 4f, 5d, 6p and 7s. You can go up to infinity. You can write down as many shells as you want to, but you have to be careful about 2 elements. The first is the copper and the second is chromium. They are really big exception here. And in chemistry, exceptions are the worst enemies and the best questions for these kind of exam. So the trap here is that copper has 29 electrons. So the electronic configuration should be like 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 and 4s1, right? But the problem here is that it does not have the electronic configuration like you want it to have. Let me write it down for you. First you will write down for chromium. What are the number of electrons in chromium? Chromium has 24 electrons. So number of electrons in chromium are 24. You don't have to write the electronic configuration of first 18 electron. You can just write down argon, because argon has 18 electrons, and from 18 electrons you can write down 4s2. Then you have, how many electrons do you have now? 20, and then 3d4. So 18 electrons, 18 plus 2, 20, 20 plus 4, 24. So this should have been electronic configuration of chromium, but that is wrong. Why is that wrong? The reason is simple, because one electron from 4s goes into 3d and it forms 3d 5 electrons. And why do we have 5 electrons in d and 1 in electron? Why is that? What is the reason here? Because d can have up to 10 electrons. You just memorize the table. If you haven't memorized the table yet, please memorize number of electrons in sp, d and f. I have given you the most basic and easy formulas to memorize these kind of things. So d can have up to 10 electrons. So imagine you have an atom that has 5 electrons in d shell, and there is an atom that has 4 electrons in d shell. So 5 is exactly the half of 10. That means the number of electrons in all the shells, in all the orbitals, in all the subshells are equal. If you write down the d orbitals, they could be like this: dx, dy, dz. Then you can have dxy square and dx minus y. So there could be 2 electrons in here, 2 electrons here, 2 here, 2 here and 2 here. That's how there are 10 electrons in 5 orientations of d orbitals. So imagine you have one electron, one electron, one electron, one electron, and one electron. This is a really stable configuration, right? But imagine there is no electron in this orbital. Then there could be like 4 orbitals, right? This, and one of these would be empty, and that would make the element really unstable. So if you take the one electron from S and use it in this subshell, that is dx minus y, it will have also one electron. So now you have a really stable configuration in which all dx, y, dz, and dx squared and dx minus y, all of these have same number of electrons, that is 1, and this electron configuration is much more stable than 3d4. 3d5 is more stable than 3d4. That's why for one electron from s orbitals jumps from s to d. The same is for copper. Copper also has like 3d9, right? It should have 3d9 and 4s2, but the problem here is that one electron from 4s2 jumps from here, like orgon 4s2 3d9, but that is unstable. The stable one is 4s1 and 3d10, because in this case you will have 2 electrons in all of these orientations. So that's why copper 29 has 1 electron in s shell and 10 electrons in d subshell. So that was the exception for electronic configuration, and now you are ready to solve any kind of question that could be asked from this topic. Like, we have literally covered everything that could be asked from this topic. That's all from my side. Bye bye, take care, and don't forget to solve all the IMAT mock exams and the full mock exam that you will be given every week. So bye bye, take care, Allah Hafiz.